nuclear fusion tech to drill deep holes. According to Quaise Energy, a startup operating in the geothermal space, deep geothermal energy is at the core of an energy-independent world. It is the only renewable solution with the potential to get us to net zero by 2050. It is renewable, inexhaustible, and available everywhere. Geothermal energy is a clean renewable energy source that has the potential to play a significant role in reducing our dependence on fossil fuels. It involves using heat generated by the Earth's core for heating and electricity generation purposes. I've already covered what geothermal is, how it is harvested, and points for and against it in depth in previous videos for those interested. I'll link all of them down below in the description box. Despite geothermal's many advantages, however, a few things have traditionally kept it from scaling up. One of these includes drilling. Geothermal energy is most accessible in geothermal hotspots. However, it is actually universally available, provided that we can drill deep enough, but this task is easier said than done. If we're able to drill 10 miles underground, we can reach temperatures in excess of 150 degrees Celsius. By going deeper still, we can exceed 373 degrees Celsius, the temperature at which water becomes a supercritical fluid and the boundary between liquid and gas disappears. This dramatically increases the energy density of a geothermal well. The challenge, however, has been and remains being able to dig that deep. Most geothermal fields today don't go deeper than 3 miles because the cost of drilling increases exponentially with depth. This is because the deeper we drill, the harder the rock becomes and the higher the temperature gets. This results in greater non-productive time as equipment fails more often. To put this into perspective, we need only look at the Kola borehole drilled by the Soviet Union. At a depth of 7.6 miles, this is the deepest borehole ever drilled and took a whopping 20 years. While they did try drilling further, they ran into equipment failures that made the task impossible. To really scale geothermal energy so it's producing in terawatts and not gigawatts, and to make it available everywhere, even beyond areas that are geothermal hotspots, we need to be able to drill hundreds to thousands of boreholes every single year. Drilling also requires a lot of money, specialized equipment, and extensive technical knowledge to, for instance, understand the thermal properties and vaporization regime of the underlying rock, and then optimize the drilling process for different types of rock formations. Conditions in geothermal reservoirs also tend to be harsh and make it challenging to maintain and repair equipment. Nevertheless, if these challenges can be worked out, in particular, the challenge of being able to drill deep, geothermal energy extraction bears a lot of similarity with the extraction of oil and gas and can leverage the existing oil and gas workforce alongside their knowledge, expertise, and experience. This is fantastic since the oil and gas industry employs people in over 100 countries worldwide, including 11 million people in the United States alone. According to Matt Hood from Quaise Energy, because drilling for geothermal energy needs the same skills as drilling for oil and gas, geothermal can rapidly be scaled to meet all our energy needs by 2050 once these challenges have been ironed out. Drilling deep, however, might soon cease to be a challenge thanks to nuclear fusion and Quaise Energy, the startup that I've already mentioned in this video. Quaise Energy proposes replacing mechanical drilling methods with millimeter wave drilling, a technique that was invented a little over a decade ago by Paul Waskoff at the MIT Plasma Science and Fusion Center. According to Quaise Energy, millimeter wave drilling will unlock the most abundant and powerful clean energy source on Earth by allowing us to drill down to 20 kilometers and 500 degrees Celsius. Millimeter wave drilling uses a device known as a gyrotron. A gyrotron is able to generate radio frequency waves. These are generated at the surface and transmitted down the hole through a metallic pipe called a waveguide. When they hit the rock is vaporized and condenses into a fine ash that can be flushed up by circulating purge gas in a process that's extremely similar to the process of air drilling. This is a widely used drilling technique in which compressed gas is used to cool the drill bit and then lift the cuttings off a well bore. Gyrotrons were developed to make nuclear fusion possible. They allow plasma to be heated to millions of degrees Celsius and create the conditions necessary for fusion to occur. To drill for geothermal, however, rock needs to be heated to just over 3000 degrees Celsius. This bores a hole through the rock and also has another desirable side effect. It melts an outer ring around the hole, which cools to form a solid barrier that keeps the hole stable and keeps fluids that could interfere with the drilling process from flowing into it. Millimeter wave drilling has been shown to be effective in low-powered gyrotron drilling in the lab and is fantastic for drilling deep boreholes for the extraction of geothermal energy since it is not affected by depth or temperature. It is also optimized for hard crystalline granite, which is a material that conventional drilling technologies truly struggle with. It is, however, not ideal for softer soils and sedimentary porous rocks that may contain groundwater, oil, or gas. Quaise Energy proposes using a hybrid solution that begins by leveraging conventional drilling technology and switching over to millimeter wave drilling when hard rock is reached. In order to achieve this, Quaise is creating the first millimeter wave drilling rigs for use in the field. These rigs can be mobile, compact, field-deployable rigs or full-sized geothermal rigs for deep drilling that integrate millimeter wave technology with traditional rig design. Quaise will complete its lab experiments within the next 2 years and then begin drilling demonstrations to start deploying these rigs for commercial geothermal projects in shallower areas. Despite the technology's positive prospects, there are still hurdles to overcome in the development of millimeter wave drilling. These include improving our understanding of the thermal properties and vaporization regimes of rocks, as well as how rocks interact with millimeter wave beams. Scaling up the supply chain to produce large quantities of high-quality, reliable equipment is also a challenge, since it is currently optimized for one-off specialized projects related to fusion research. Finally, technical difficulties that arise during actual drilling operations, such as removing ash from the borehole and maintaining stability at great depths, also need to be addressed before geothermal energy can become truly scalable. Nevertheless, given all the recent capital flows and new developments in geothermal energy, its future is looking increasingly bright. If you enjoyed this, please do subscribe to the channel to be notified for when I post next. Please do also leave a thumbs up and hit the notification bell, and I'll see you in the next video.